We're going to continue on with spring examples, but this time we're going to look at a damp spring. And we're going to talk about sort of a model with general numbers first, and then we'll do a few that like actually plug in specific values. So the equation for a damp spring, hopefully you remember it, was m times your second derivative plus beta times your first derivative plus k times your displacement x, where this is sort of describing your damping according to the speed of the mass on the spring currently. This is your spring force as usual, and that came from your Newton's second law. And I'm going to rearrange this because solving with something on our highest derivative can be difficult, into this form. And then beyond that, what I'm going to do is I'm going to just introduce some like placeholder variables. And I promise it's going to like be for a reason later. But I'm going to create this new thing called lambda, where 2 lambda is just beta over m. So lambda is beta over 2m. And I'm going to create this thing omega squared, where omega squared is just k over m, or omega is the square root of k over m. And the reason I'm doing that is so that when we factor this auxiliary equation we get from this type of problem, things are actually a little bit neater. But to solve this equation, I will let x equal to e to the m times t. So then x prime is m e to the mt, and x double prime is m squared e to the mt, and the ODE is 0 equal to m squared e to the mt plus 2 lambda m e to the mt plus omega squared e to the mt, or m squared plus 2 lambda m plus omega squared times e to the mt. And the auxiliary equation is 0 equal to m squared plus 2 lambda m plus omega squared. I know that having all those variables for the parameters instead of numbers can be sort of intimidating, but the reason we're doing it is so that we can see sort of different behaviors that emerge. So the solutions we'd find from the quadratic formula would be m equal to minus 2 lambda plus or minus the square root of 2 lambda squared minus 4 times omega squared all over 2 times 1. So that's going to be equal to minus lambda plus or minus a half times the square root of 4 lambda squared minus 4 omega squared. What's minus lambda plus or minus 1/2 square root 4 times lambda squared minus omega squared. And I can go ahead and factor out that square root 4 just to give me minus lambda plus or minus the square root of lambda squared minus omega squared. It was just that 4 became a 2 out in front and canceled with the half. Okay, so now we can kind of start to think about what's going to happen when we actually plug in numbers and try to find m. So there's a couple different cases that could emerge. If lambda equals 0, we have no real part, and m would be equal to plus or minus the square root of minus omega squared, which is like we had before. We would get sine solution and cosine solution. And if lambda is 0, that means that beta was 0. So really we're just saying if we ignore the thing we just added to the equation, we get what we had before, which makes sense. If lambda doesn't equal 0, then there are 3 options. And they're all going to have to do with what happens inside that square root. So if lambda squared minus omega squared is less than 0, then there's going to be an imaginary part. We're going to have m is equal to alpha plus or minus I beta for beta equal to the square root of lambda squared minus omega squared. Well, really, omega squared minus lambda squared. So if lambda minus omega squared is less than 0, this number is negative. So then you're going to have I times the absolute value of it. Oh, I bet absolute value will be less confusing to you when you're doing this. Like that. And so we end up with those complex conjugate pairs, alpha plus or minus I beta. If lambda squared minus omega squared is less than 0, then square root lambda squared minus omega squared is a real number. And so you get just 2 real numbers, m equal to sort of m1, m2 real numbers. And that gives us that e to the m1t, e to the m2t that we started our examples with, whereas this option gave us those complex special cases that we introduced later. And then the sort of middle case is if lambda squared minus omega squared equals 0, then we only have one root. M equal to minus lambda. This leads to repeated case where we get like e to the minus lambda t and t e to the minus lambda t. And so this is sort of demonstrating that when we have one of these damped spring systems, the relationship between lambda and omega, that is the relationship between beta and k really, because both depend on m, is going to tell us about 3 different behaviors that can emerge, or 4 if you consider beta not existing at all and just going back to an undamped system. So in the next video, we'll go ahead and do an example that shows each of these things so we can see the 3 different types of behaviors that come out.